What up in my real earth chatterbox? That's an old line. That's an old line. But I want to show you how we get from the real world, where things really are, the things that we can touch, smell, and the places we actually inhabit, to these maps that have location. There's a process to it, and this thing is called a geographic coordinate system. Sometimes it's called a reference system. And as you'll see in the activities you do, they're a little bit different depending on where in the world you're mapping. So you can see here that we go from the real Earth surface to a mathematical model to a model of the Earth in which we drop a graticule on. How does that work? Okay, so we pick a datum, right? A datum is this way that we transform the real Earth surface into a map. Map. So we have this datum here, okay? And this is based on a real measurement of the Earth's surface. The Earth's surface is like not smooth. It's not a circle. It's not a globe. It's roundish. It's an Earth-shaped object, which is called a geoid. I'll go off a little bit on the flat Earth people. This is something, actually, you know what? We'll have a conversation on Slack. I think that will be more fun. So this is the real Earth surface. Let's say this is North America. And so we end up using what's called like NAD 83. Funny, I saw this scrawled in the men's bathroom. And where did we used to have class? Yo, seriously, it's been so long. I want to call it Powder Maker Hall, but that's where I used to teach years ago. Gladfelter, yep. Gladfelter bathroom. I saw NAD 83, right next to the anarchy symbols. It's cool. So this is a mathematical model for measuring what the shape of the Earth's surface here is in North America. Because depending if you have mountains, trenches, volcanoes, oceans, the Earth's surface is going to be different. So we have a real measurement of what that place is, and then we pick a mathematical model to account for that. What we're doing is we're simplifying the surface of the Earth into an ellipsoid. This is the magic of math. We are using an equation. We are simplifying the real measurement of the Earth. It's still preserving important parts of it, so our geographic location is accurate, but it's getting rid of other stuff. The ellipsoid, or the circle, right, are mathematical concepts. There's no such thing as a perfect circle. It's a way that we have invented, a way of problem solving, a way of building bridges, of engineering, right? And we use this to geographic location, to navigate, to get from one place to another. This is a big problem for human beings. How do we get from one place to another? And we solve this problem with things like this, right? And this was a model already in place, but now a computer does it easier, and we have GPS, which we've just had for the last 50 years. But this is what maps are based on. So real surface, measure it, transforming it using a customized mathematical model, customized based on real measurement. And then from that ellipsoid, we create a map, which is like a representation of the world. And then we drop the latitude and longitude on it. Now, when you do your exercise, you'll see when you switch the datum around, right? You're going to switch the datum around. You are going to get slightly different locations because it's based on different measurements of the Earth's surface. So we always want to pick a geographic coordinate system that is close to where we're mapping. NAD 83 is one of them. WGS 84, World Geodetic System in 1984, and this is good for the world. So depending on where we're mapping, we pick a model of the Earth's surface based on the location that we're mapping in. And through the power of math and ellipsoids, we simplify that, and then we create a model of the Earth, and we drop latitude and longitude on it. And that becomes our grid and the basis of knowing where we are.